Okay, so it's 2 now. Let's get started. I'm seeing a lot of people, almost 40 people are joining this seminar. I'm sure the number is continue to soar up. So hello everyone, welcome everyone to Ask Seminar series. I'm John, the seminar coordinator. I will be moderating this seminar with Cassie Medley, who is our communication specialist. And this seminar is being recorded, and we will publish the video recording on our YouTube site. Please feel free to ask any questions after the presentation. You can do so by unmute yourself and speak out and out. Before the speaker gets started, I will hand this over to Cassie to introduce the speaker. Cassie, please proceed.
Thanks, John. So today I am substituting for our director, Ralph Ferraro, who's out of office today. So I am pleased to present Dr. Stephen Greybush. So he is an associate professor in the Department of Meteorology and Atmospheric Science and a co-hire of the Institute of Computational and Data Sciences at the Pennsylvania State University. His research applies computational techniques such as computer simulations, data assimilation, ensembles, and machine learning to study the weather of the Earth and Mars from snowstorms and other extreme weather to dust storms. He obtained his undergraduate degrees in meteorology and computer science from Penn State and an MS and PhD in atmospheric and oceanic sciences from the University of Maryland, go Terps. His teams produced the first ensemble reanalysis of the Martian atmosphere, which provides hourly maps of temperatures, wind, surface pressure, and dust across Mars for a period of over a decade. He leads the executive team for the Penn State Center for Advanced Data Assimilation and Predictability Techniques and is a member of the Multi-University Consortium for Advanced Data Assimilation Research and Education. So I'm just going to go ahead and turn it over to Dr. Greybush. So please proceed. Thanks, everybody, for coming.
Thank you very much for the kind introduction. It's great to be able to give today's ESSEC seminar. I'm going to be looking at first introducing the ideas of data assimilation, predictability, and AI, and how they all link together. And I'll be doing that by first looking at snowstorm predictability and ending with severe weather predictability. I'd like to thank all my colleagues who have worked on this with me, including grad students listed above, Da, John, Song, Ethan, and Christian, as well as faculty collaborators at Penn State and elsewhere. So at Penn State, I am the executive team lead for the ADAPT Center. So I just wanted to introduce that at Penn State, we have several faculty members working on data assimilation and predictability problems. These can span the snowstorms and severe weather that we'll talk about today, but also include tropical cyclones, idealized models, and applications to hydrology and even the Martian atmosphere. We're also part of a cadre consortium. So this was announced by NOAA this year, and it led by University of Oklahoma, but with teams at Maryland and Penn State and a number of other universities. The goal is to work with NOAA to improve data assimilation, as well as train the next generation workforce in data assimilation among our students. So let me start by introducing data assimilation. So in key conceptual ideas is that to get better forecasts, we need better initial conditions. And data assimilation does that by estimating the state of the system by combining a prior field or background, usually a short-term forecast from a model, with observations. And it does that in three important ways. First, by weighting the information according to their uncertainties in a Bayesian framework. If we trust an observation more, it will get a heavier weight. Secondly, it spreads that information across different variables and in space using covariances. And that can incorporate kind of the physics of the problem. Next, it then spreads that information dynamically through time using a forecast model. And in the ensemble paradigm, we start from a data assimilation system here on the left, and then we launch an ensemble forecast, each a different copy of a model. And from there, we can estimate how confident we are in a certain forecast or solution. Those ensemble forecasts then provide the flow-dependent information back into our data assimilation system. But we keep this ensemble forecasting forward in time. And then eventually we're able to compare to what actually happened at some key time, let's say for a snowstorm. And at some time further in this future, we know due to the butterfly effect or chaos, we lose predictability for an event. So it's important to be able to characterize how well we are representing the uncertainty in an event through ensembles, as well as at what stage for different phenomena do we lose predictability for an event, or when have we reached the predictability horizon. So this is a classic paradigm used for traditional numerical weather prediction, but we also want to think, how does AI relate to this paradigm and give new innovations and insights? So let's start with the traditional numerical weather prediction paradigm. And what we're going to do here is gradually introduce data-driven or AI approaches to different places in this paradigm. So we're starting with the numerical weather prediction model that has physics parameterizations in it and a data assimilation system. And in all of these, we can really think of mapping inputs to outputs, whether the inputs are our observations that we measure of the Earth system and the outputs being a prediction. Okay, so traditionally, we've post-processed numerical weather prediction forecasts. It could be something as straightforward as multivariate linear regression, or MOS, that's been used for decades, more complex machine learning. We could also do uncertainty quantification by including an ensemble to know how confident we are. We see also that this is representing that uncertainty quantification to get basically a PDF around a solution. We could also do uncertainty quantification as well as post-processing. For example, the analog ensemble technique that's been used for weather. We can also use machine learning to replace different physical parameterizations as part of a numerical weather prediction model, because these predictions can be much faster than the original. Another place to consider using machine learning is for the error covariance modeling. That's how we spread that information across space and across variables in the data assimilation system, or by using data assimilation to update physical parameters inside a model. Okay. We can continue to use that paradigm for different types of hybridization of data assimilation and machine learning. We can think about replacing the forward model that, for example, looks at taking a model field, let's say temperature and moisture, and produces what the satellite might observe to speed that part up. And then finally, more recently, there's been replacement of the entire numerical weather prediction model with machine learning models. But those still rely on data assimilation to produce the initial conditions. These would be models like the Pangu Weather, ForecastNet, or GraphCast. We'll show some of these results in later in the talk today. And then another approach is to go directly from observations, kind of bypassing the data assimilation step. And this can be used for nowcasting directly from observations. And we'll show some results of this applied to severe weather at the very end of the talk. So thinking about the winter storms aspect of the talk, what are the key questions we want to ask? So we want to look at practical predictability. That is, given our current limited observing system and our current imperfect models, how far ahead can we skillfully forecast a weather phenomenon? Right? And this can be the synoptic-scale evolution of a storm, or the mesoscale features like snowbands or precipitation transition regions. What do the ensembles reveal about physical and dynamical mechanisms that limit predictability? And how well does the ensemble spread correspond to forecast error? And how well can convection-allowing NWP and assimilation of additional obs help better constrain winter weather? So some motivating cases that kind of got this part of the research going were two big snowstorms in January 2015 and 2016, right, bringing 25 to 100 centimeters of snow through the major cities of the East Coast. The 2016 storm, I'm sure, is well remembered by those living in the DC area at the time. The prediction challenge for these storms was immense. So these were operational model forecasts for the 2015 storm for Boston, indicating a high confidence of 25 to 40 inches, as well as a prediction for New York City, indicating 5 to 40 inches of snow. Now, this is an extreme range of potential snowfall outcomes. So that really motivated the question, is that extreme range of outcomes appropriate? And if so, what is driving the extreme differences in potential outcomes? So what we did to examine this question is create a type of diagram called a predictability horizon diagram. So here on the right side of the diagram is the event total precipitation. And as you're moving away further back in time from the event, you're getting to longer and longer forecasts. Each dot here is an ensemble member forecast. So you get a sense of how big was the ensemble agreement and how far into the past was their ensemble agreement for an extreme event. For Boston, the storm was very well forecasted several days in advance, whereas New York City, even a short-term forecast still had considerable uncertainty. So the next step was to try to investigate why there was that uncertainty. So first of all, we did ensemble sensitivity analysis. We learned that the position of the low pressure system off the East Coast tightly controlled a western gradient of precipitation that was very tightly clustered through the New York City area. So a storm slightly further offshore would keep the heavy snow over Long Island, whereas a track further inland would bring that all the way in toward Philadelphia. And these are very small shifts in the East Coast winter storm track. So what can cause the uncertainty in the track? We can do a correlation across ensemble fields between the track of the storm and the 500 millibar height field, seeing that uncertainty in the 500 millibar height field at 24 hours in the past. And if we track this, it would be 48 hours over the Midwest, maybe 72 hours over the Rockies. That was a leading driver uncertainty in the synoptic scale low pressure location. And then looking at the 2016 storm, again, here is the example of Dulles, where 3 to 5 days in advance, an extreme event was forecasted. Whereas New York City, once again, was right on the outside edge. And you could see for Dulles, looking at these diagrams, we looked at 3 timescales for prediction. The initial detection of an extreme event, where maybe 1 or 2 model solutions hints that an extreme outcome might be likely, or possible, I should say. The second phase, where a signal has emerged where the ensemble mean is now showing that there's an extreme event possible, but there's still multiple scenarios, a low end and a high end. And then hopefully we get to the convergence of solutions stage, where the ensemble members all agree on an outcome. Here, once again, New York City had that wide divergence of solutions. Last case was when the city was shut down, but only got a foot of snow. This next storm, a year later, they set their record in Central Park. So we could see that in these ranges, because New York City is right at the extreme edge of the heavy precipitation, the synoptic scale and mesoscale uncertainty actually led to this very large range of precipitation, possible outcomes. And looking at a reliability diagram, for these extreme outcomes, we actually see that the ensemble was underconfident across space, saying that, yes, these extreme amounts of ranges of outcomes are appropriate and perhaps even underestimating the potential outcomes, given our current initial conditions and models. So we then went from operational models to running our own convection-allowing simulations, kind of highlighting the snowband through eastern Pennsylvania and the New York City area. This paintball plot kind of showing locations of heavy snow and where that mesoscale band would set up. And in the 2016 storm, even if the synoptic details right, the exact details of the mesoscale band became important. And in other experiments that we did for lake effect snow off of Lake Ontario, this is upstate New York, the placement of a mesoscale band was very sensitive to the exact wind direction that we were seeing. So here, trying to get the uncertainty correct, you have to consider uncertainty at the synoptic scales. That is from the situation, let's say the low pressure area and wind pattern, maybe even driven by outside the domain at more than 24 hours in advance. The mesoscale uncertainty, the wind field and convergence at local regions, and then model error, okay, which leads to differences in intensity of the precipitation, even if you get the lake effect band correct. And this band forecast for these lake effect bands, as well as East Coast winter storm bands, still exhibit considerable uncertainty in, let's say, the 12-hour forecast lead time, which is something we hope to be able to improve in the future. And we can see that uncertainty is very sensitive in this object-based diagram to very small changes in the wind field. From a wind from 255 degrees to 270 degrees makes the difference if a location gets heavy snow or not. So we can see the importance in characterizing specific objects that the human eye or the human forecaster uses. So in this work here, we used the geometry-sensitive ensemble mean to better represent objects. So for example, imagine that you had a snowband or cloud feature that was at a slightly different position in different ensemble members. In the simple arithmetic mean, you end up with a washed out signal that looks like you have a circular feature here, but at a much lower intensity. That would not be a good representation of the ensemble. Whereas with this geometry sensitive mean, we're able to get a mean field that's actually kind of taking the spatial displacement and moving these together to the same location, but preserving the intensity. And we were able to demonstrate with that with lake effect snow cases and others. So finally, now we come to NASA impacts, returning to the East Coast Winter Storm Challenge. And this, we had a wonderful opportunity with many collaborators at University of Washington, Illinois, and NASA Goddard, and many other places. And this field campaign flew into East Coast winter storms in 3 field campaign years, 2020, 22, and 23. And there were 2 aircraft tracks. First, the P3 that flew through the precipitation and measured the cloud properties as well as in situ temperature and moisture. And then the high-flying ER2 that flew over it with downward pointing radar, we were able to get radar retrievals of wind velocities. And they targeted these snowband regions and other intense regions of the winter storms as they flew. So we did our own ensemble modeling and data assimilation with a configuration that's somewhat similar to the HER, high resolution rapid refresh, but on a smaller domain scale that we could afford to run at a university. So kind of a 9-kilometer outer domain and a 3-kilometer inner domain at convection-allowing scales, and kind of initialized it through the extent of a few different NASA impacts cases. And we did data assimilation hourly using the Ensemble Kalman filter and assimilated conventional observations. So for example, in this plot, we can see surface observations available during this 2022 storm, which I'll talk about in a moment, as well as the commercial aircraft observations. So for this storm, this was one that had high impacts on New England, bringing flooding, coastal flooding, as well as very strong winds to Boston and coastal Massachusetts, as well as heavy snow bands. So this is showing the NEXRAD observations on the top row compared to our simulations from a deterministic run and an ensemble run. So this is kind of the baseline that we're going to then improve upon with our own data assimilation here. And for here, you can see the NEXRAD observations showing this heavy snow band through Boston at this time. So getting even if we get the synoptic details of the storm, getting these mesoscale details of a snow band is challenging. And we could see it through these neighborhood probability plots. So this is saying that looking across an ensemble of 40 members, how many ensemble members or what % of them have simulated radar reflectivity greater than 20 dBz, in other words, moderate to heavy snow. Right? So you can look at particular members. For them, so this member has a heavy snow band through east central Massachusetts. Here's another one that's going over Massachusetts through Maine, kind of matching this one perhaps best. But overall in the ensemble, there's a bifurcation between members that have heavy snow over Massachusetts versus others that keep it offshore. So we'll come back to this 2022 case in a little bit, but now we're going to go to a 2020 case, also from NASA impacts. This was more an interior storm that brought heavy snow to upstate New York. You can see the snow totals of 6 to 12 inches here over upstate New York here. And the track of the storm is through the interior of New York. Now, why we looked at this storm is because here NASA impacts was flying through heavy snow over upstate New York. And we wanted to see if assimilating special observations from NASA impacts was able to improve the mesoscale details of the snow forecasts. So just to zoom in on this area with the NEXRAD radar presentation, this is around the time of the flights. We can see this is comparing to the New York Mesonet data at Elmira, New York, which is about here, where my cursor is located. And we can see the snow depth rapidly increasing as these heavy snow bands move through. Okay, so this is a key feature that we want to be able to model and improve through data assimilation. So here's some examples of operational NEXRAD radar versus the XRAD downward pointing radar from the storm from the field campaign, as well as the model reflectivity. So what we're going to do here is we're going to assimilate in one experiment only conventional observations, including surface observations, sondes, and commercial aircraft. And then we're going to have a second experiment that assimilates NASA impacts observations. That is conventional and XRAD retrieved wind field, as well as in situ temperatures, which is a great to have during the storm. So from here, we're going to do some comparisons. First of all, a domain-wide comparison, and looking here at reflectivity. So remember, we haven't assimilated reflectivity, but instead we'll use it to say, did we update the model in a successful way in the wind and mass and microphysics fields so that we can hit better reflectivity to compare to the operational radars. Okay, so we used root mean square error, bias, and critical success index for a 20 dBz threshold. And we can see that overall, the aircraft and aircraft free run, that is after we stopped assimilating but launched a forecast, that's the blue and purple curves, are generally better than the other two, right? But at a domain-wide, we don't see a statistically significant difference at most lead times, but we do generally see a better outcome. So let's just now zoom into a closer location. Okay, so we're going to zoom in on that upstate New York. Again, this is the baseline run showing kind of heavy precipitation here, but maybe missing having some extraneous rain bands here in the New York City area. And we're going to compare our two experiments. So the top row here is with NASA impacts data. The bottom row is without NASA impacts data. And we can see that when we assimilate the NASA impacts data in upstate New York, we're leading to a greater neighborhood probability of high dBz radar reflectivity. So it's helping to fill in the missing heavy snow, which is in a critical area here over upstate New York. Right, to better see these, let's instead plot the difference field. So red is saying that the aircraft experiment had higher radar reflectivity in these particular regions. And we can see that here, that this is the radar signature showing these heavy snow bands at that same location. Okay, we can take another look, again, comparing the air to COMV at a particular time. And what we're doing here is we're trying to now look at how the updates to the dynamical microphysical fields propagate to improve these radar snowband features. Okay, so we've taken these domain averaged features, but a better way to approach this might be an object-based approach, like we showed earlier for our geometric ensemble mean. So in active research right now is this geometric ensemble, this single liquids clustering snowband tracking. So taking a radar or model simulated radar feature and being able to identify particular band features. And from there, we're going to be able to come up with an object-based approach to look at the performance of our data assimilation system. Another way we could further explore is to, first of all, learn what we can learn about the microphysical characteristics of winter storms. In particular, this is an example from a previous paper by Kumjian and Lombardo, looking at vertical cross-sections of radar. This is horizontally polarized bright band, so this tells us there's a melting layer in progress. We can see that correlation coefficient, as well as there's a correlation coefficient reduction in the dendritic growth zone. So if we're able to determine dual pole signatures of specific thermodynamic environments, that might give us additional observations to assimilate, even when there's not a field campaign going on. But what we're going to do here in this study is to be able to look at the microphysical signatures of dual pole and be able to compare them to temperature measurements from the field campaign. This is the work of Song Jiang and Matt Kumjian. And so the idea here, this is a horizontal cross-section here at a particular elevation angle, I should say. And this is ZDR and correlation coefficient. So since we have actual flight data flying through this region, we can look at the thermodynamic environment along these flight tracks where they match up vertically and temporally with the radar. And we can see kind of these different temperature ranges. For example, the dendritic growth zone near -15 Celsius, or needle growth area, or others. And in Song's work, that she's looking to look at these different zones of temperature as seen from the aircraft and compare them to the dual pole signatures that we see from the WSR-88D radars. And then from those radars, first we're going to characterize the microphysics, and then eventually hopefully be able to come up with an algorithm that detects these unique microphysical signatures. And we hope to be able to eventually use that for data assimilation. Okay, some other things that we can do here is we actually have images of snowflakes that were sampled during the NASA Impacts Field campaign. So from here, we can look and see, well, do we have dendrites? Do we have melting snowflakes? Do we have plates? And other characteristics, as well as aspect ratios, crystal sizes, and others. And we hope to use this rich data set to, again, improve our modeling as well as our microphysical understanding. Okay, so for the next part here, we're going to return to the predictability question. So this is back to the January 2022 case. But now we're going to bring in AI forecast models as well as the traditional operational forecast models. So in this plot, what we're visualizing is the 2022 storm, low pressure location, that's the star here. And as you go back in time, right, you're getting different locations of the low forecasted from the GFS, which is physics-based, and then GraphCast, Pangu Weather, and ForecastNet, all of which are using AI models to approximate the physics. But they really just learned it by using reanalysis data, matching inputs to outputs. And so you can get a sense for the track errors. And remarkably, the track errors are really good here. So they're even beating the GFS here as far as track here as a function of track error at different lead times. You can see lead time going from short range in the dark colors to further out in time in the light colors. We're going to also look at different model fields from the GFS and these other operationally kind of run AI models, and also hindcasts of AI models. So again, these are different AI models run by different groups, the GraphCast, ForecastNet, and Pangu Weather. This is now looking at 500 millibar heights, another field that's really familiar to forecasters. And we can see the initialization for each of these looks similar, as do the 72-hour forecasts. But remarkably, the GFS 168 hours is not capturing the deep trough needed for this storm, whereas GraphCast and Pangu Weather do have a deep trough. So interesting that these AI models might potentially increase the practical predictability horizon for the storm. Now, this is looking at the deepness of the surface low in hectopascals. And you can see that these AI models are a bit coarser in resolution compared to the operational GFS. So that's one thing that they're going to struggle with, is with small scale features. But we can still take a closer look at minimum sea level pressure. Right? So this is, again, a predictability horizon diagram from minus 168 hours leading up to the actual time of the storm. And we can see the GFS and one standard deviation plus or minus in its ensemble in this black curve in the shaded area. And you can see as you go further back in time, there's weaker surface pressures generally. But interestingly, these AI models still have a strong storm in the domain at these longer lead times out to 168 hours. And then here in red is the Euro model comparison. Okay, so I would say this storm was fairly well predicted by all models. I think a challenge for the community now is to be able to assess what are the strengths and weaknesses of the AI models and how do they compare to the physics-based models. Okay, we could also look at this at a number of storms. This is a sample size of about a dozen storms. We're comparing the GFS, the Euro, and then 3 different AI models. So this is at 24-hour lead time. This is root mean square error for 500 millibar heights, going out to 72 hours lead time, 128, 168, and so forth. And you can see here that if I covered the key here, the AI models are competitive with, even at these longer lead times, with some of the operational models, which is very interesting to see here. So we're just starting to explore this question, but we're interested to know how these AI models will be able to enhance predictability. So for the winter storms part, we're going to conclude here by saying that the predictability horizon diagrams and ensemble sensitivity analysis can help illuminate the predictability challenges with East Coast winter storms, as well as lake effect snow. And we can apply these to the traditional NWP, but just recently we're now applying them to the AI-based models to help assess predictability. We've also done our own ensemble simulations of East Coast winter storms and assimilated NASA impacts observations, and we're trying to get a sense of how that enhances the mesoscale predictability of storms. And predictability can be limited both by synoptic-scale factors, which might have a several-day lead time of skill, as well as mesoscale features, which might have a limitation of skill to less than a day. Snowbands and other mesoscale features are critical. So going forward, we're looking and quantifying the predictability of more cases for the NASA Impacts Field campaign, as well as further developing the snowband tracking algorithms. We're also looking at ensemble microphysics sensitivity. We have a grad student looking at sensitivity to different microphysics. And Ethan's also hoping to improve through the modeling, through parameter estimation, which takes information from the observations and feeds that back to uncertain model parameters. We're also continuing with Song's work with the dual pole radar signatures for various temperature regimes. And hopefully someday we'll be able to potentially assimilate those signatures. So for the last part of the talk, we're going to move to a different application area, but use some of the similar kind of techniques. And that is looking at predictability, ensembles, and AI. So here we're pivoting from winter storms to convection initiation. In other words, which cloud features seen in this upper domain might develop into severe thunderstorms, or more generally into deep convection. So the idea is to first be able to identify storms. So we can see here, this is a radar image. We want to be able to identify when does a new cell appear, and that we would call a CI or convection initiation event. And by tracking that, we know that sometimes convection can lead to severe weather, such as hail, tornadoes, damaging winds, and flash flooding. And you can use the traditional numerical weather prediction approach, but a challenge can be elevated false alarm ratio. You can have missed forecast. You can also have challenge of spin up. And we'll just give an example of numerical weather prediction-based approaches. So we're here going to instead use a pure machine learning approach using deep learning to try to predict which clouds develop into these CI events, as well as quantify the uncertainty, like we can with ensembles, as well as interpret the dynamical insights. So for this deep learning project, let me just back here, what we're comparing against, right? So the state of the art on the numerical weather prediction side is something like the high resolution rapid refresh or the other convection allowing ensembles that are either run operationally or run in-house here at Penn State. So this is an example from the Penn State ADAPT group showing how we can use both satellite data assimilation as well as radar data assimilation conventional observations to better represent CI. It's a challenging problem, but we've had some success here. But now we're going to kind of look at the machine learning side of this. So for here, we're going to define CI by this definition from Colbert et al. Okay, so composite reflectivity basically greater than 35 dBz and some special criteria to identify new convection. We're going to make it even more challenging. Not just are we tracking existing convection, but where is new convection going to occur? So there we have to track these CI events into tracks and identify which ones are new ones that are not part of an existing storm track. And then what do we want to predict? We want to give a probability of whether new CI is going to occur within a 48 by 48 kilometer patch in the next 10, 20, 30, 40, 50 minutes. So what do we use as our predictors? All right, here we're going to use the GOES-R infrared and including water vapor channels. So 7 GOES channels, and we're going to use spatial images. For example, this is what the CI event might look like in the satellite image, where you have warm brightness temperatures surrounding the storm and cool brightness temperatures with the high cloud tops associated with the storm. So we used training events, about almost 100,000 training events over the Great Plains. And the training events consisted of about half of them being CI events. Most of them are near misses, about 40%. That means areas that are near CI, but close by. So in other words, which of these are in a severe weather environment, but pixels that aren't developing the CI? And then finally, which of these are random events, that is randomly chosen pixels? Those are only a small percent of our data set. So we're really trying to look at the challenge of which clouds are going to develop into new convection. So we did our training and validation data sets in June and July 2020 and testing in June 2021. Okay, so what's the methodology that's used? So many of the listeners might be familiar with linear regression or MOS. We're going to start with that and build our way up to the ResNet architecture that was used here. So if you take a linear regression algorithm and you add a nonlinear activation function, right? Y equals A1 times x1 plus a2 times x2, all the way out plus a y-intercept. And then you multiply that by maybe a hyperbolic tangent or a sigmoid function. That gives you logistic regression. Again, can still be used in MOS. When you add multiple nodes of these together, you get a neural network. So this logistic regression node is kind of a single neuron. A neural network is putting together most of these into a network that would be maybe state-of-the-art in the 1990s. A neural network with several deep layers gives you a deep learning network. So these came around about 15 or so years ago and are very good at image recognition. And then deep learning, where you only have partial connectivity. And instead of having a connection from every possible pixel in the image to your output, here we're looking at tiny parts of the image at a time and looking for particular patterns. And then from there, that gives us a convolutional neural network. And finally, the particular architecture that we're using here that connects from the inputs and then also has some skip ahead features that gradually come down to a single prediction. This is a ResNet. And so we're going to be using a ResNet for this work, which was done with Dafan, former grad student, and David John Gagne. Okay, so looking at some of the performance, we use area under the curve, critical success index, false alarm, and Breyer score. And we're going to compare against a basic logistic regression. In other words, how much improvement can we get by using spatial information? And we could actually look at some predictability diagrams in a sense, or how do the skill of this prediction change as a function of lead time? Okay, so we can see a really good critical success index at a time scale of 10 minutes. But as we get out toward an hour lead time, that skill is kind of asymptoting. And we actually have a really nice exponential decay that we can fit to these data points to show how that skill decreases over time. We could also look at the rock curve. So in these diagrams, the closer you are to the upper left of the diagram, the better. We can see the ResNet outperforming logistic regression. We can look at the performance diagrams. Again, the upper right in this case would be better, critical success index. And then we also look at the reliability diagrams. In other words, does the forecasts mean what they say? In this case, you want to be closest to the diagonal as possible. We can see these are fairly reliable, more reliable than the logistic regression. Okay, the next step here is we want to try to see, well, what is the machine learning algorithm using to try to make its predictions? And does this match the intuition of a meteorologist? So let's look at a single example. So first on the bottom, this is a simulated radar. This is radar reflectivity. So at 0 hour, we have a 35 dB Z signature. That means we have CI. Looking back in the last row to the second to last screen, we see a weaker cell. And if we go back 30 minutes, there's nothing on radar that tells us a storm is going to form there. But if we look at our satellite image from visible and cloud albedo, we can see that there is a cloud present that's tracking through the domain. And we see that as well in the cloud seed and the IR, as this cloud top generally grows in height. And we can see also the signature in the water vapor channels as well. So how can we see what the machine learning system used? Well, we're going to use explainable AI or XAI to do that. And one particular method is this partition SHAP method. And in this example, for example, like if you're looking at a bird image and asking a question, what part of the image did we use to find the bird? Is it the eye or the beak or the kind of the shape of the bird? This SHAP method is going to look at pixels in the image and see which of those pixels contributed most to giving a good prediction. Okay, so this is now kind of looking at some examples. And how this partition SHAP works is we want to say we can make a prediction based on a baseline image. In other words, a generic image that doesn't have CI. It's just maybe a background field that has warm brightness temperatures or no clouds in it. And then as we replace parts of our image with the baseline image, right? Let's say taking our example that we looked at for some successful predictions, and let's say we replace part of the center with a warmer cloud top in our IR channel. How would that change our prediction? Okay, that's going to give us a SHAP value. So what we're seeing here now are differences from the baseline. Okay, so this is 3 different baselines that we could potentially use. And we can see that in the cases where we have a positive successful identification of CI, you're going to generally have colder cloud tops. Okay, we see that in our difference field. And then these contours are showing us where the algorithm is focusing. Positive means it's a positive contribution if you replace the image with the baseline. So in the center of the image, it's zeroing on a 7.3 micron brightness temperature channel near the center of the image in several of the channels. Okay, we can see that here, here, and here. And from that, we get a sense of what parts of the image might be important, as well as which channels are most important. You can see the total CHAP values are strongest in the 6.95 micron channel, the 7.3 micron channel, and the 11.2 micron channel. So we could also look at some uncertainty quantification. So in other words, when we do a prediction for CI, we're going to get a probability of what the amount of the odds of having CI in that square are going to be. So we would hope that when there's a high probability, let's say 90% chance of CI, then we have more successful forecasts. And same thing, if you have a low probability of CI, we have many of those are also correct predictions. So you can look at a potential animation here, getting a sense that we should hopefully have more correct predictions. That is a dark green with a black dot, as well as a light green with a white dot. Okay, so this is giving some examples, but we want to be able to test this over many cases. And we also want to look at different ensemble approaches for deep learning. So our initial approach was like using a single numerical weather prediction model forecast, except here it was machine learning. But what we now want to do is look at how can we do ensembles of deep learning systems. Okay, so there's a few different ones. One is by doing initial weights. Okay, so in a machine learning algorithm, you have the weights on how do you weight the different inputs coming into a neuron. This would almost be like different kind of an initial condition ensemble. You also have Monte Carlo dropout, where you drop out different neurons and see how that impacts the result. And you also have Bayesian neural networks that actually try to come up with a distribution for weights. And so some ongoing work that we're looking at is how well do each of these different types of machine learning networks quantify uncertainty. So this is a different way to look at those different algorithms. So first, our deterministic is kind of imagining in your hypothesis space, we have a single forecast, this red dot in the center. The Monte Carlo dropout would be like you're exploring similar solutions here. The Bayesian machine learning looks like you now have a PDF space here. In this other one, Bayesian moped, you're now recentering it around the deterministic. So this would almost be, has analogy to kind of recentering an ensemble around our deterministic solution. And then you have some other types, this deep ensemble plus Monte Carlo, where you're varying the initial weights. Okay, so we can compare these different ensemble approaches as a function of skill store. And we're seeing that these are actually able to, many of them do better than the deterministic outcome as far as the Breyer skill score. And then so coming up to the future directions, where do we want to take this? So this project has successfully demonstrated a deep learning approach to CI with superior performance compared to a classic machine learning approach. And we looked at interpretation and also uncertainty quantification. So we now, as part of the NSF CIIG program, we're now going to keep exploring ensemble approaches and uncertainty quantification. We want to look at the physical interpretation of these, look at the NWP fields as a function of input, and try to actually use not just satellite, but for example, the HER as an input to the field. We'll look at the best hybrids of NWP and machine learning, and also try to compare predictability horizon paradigms across numerical weather prediction and machine learning. So at this point, I will stop and take some questions.
Thanks, Professor Greybush. So Lisa had a question a couple minutes ago, so I'm just going to let her start off our Q&A.
Yeah, try to find it. Unmute here. Hi. This was really interesting. I'm especially interested in the snowstorm prediction part. I do snowfall estimates from observations from satellites. I've been a little bit involved also in the impact field campaign, and I have this feeling that usually what we do and what you guys do are kind of compartmentalized. So we do our observations and estimates. You do your predictions using, ground-based data or balloons or whatever you have available. Is there any way, or how do you see satellite products, precipitation products, specifically snowfall products, help, or what should they have to actually be included in your prediction?
Great. So
Can
there's
they?
two ways that's an excellent question. Two ways I can think of. So one is at a data set that we might be able to consider assimilating at some point in the future. So for that, so a lot of the classic numerical weather prediction went from using retrievals directly to the radiances. But potentially in some cases, a retrieved product with experts such as yourself and others know the nuances of the data and perhaps might be able to extract some better signal that we could potentially use. So what we would like is the timestamp, lat and lon, but also an uncertainty estimate. Because when we do data assimilation, we need to know kind of what error bars, how much do we trust the model versus the data assimilation. And then we need some type of forward operator. So if it's some product that's telling us about some properties, maybe it's total snowfall or some properties that you're getting about the ice crystals, how do we take our model output and our microphysics, even though we might not have everything we need in the microphysics, and map to the product that you might have? And then that's kind of what would need for potential data assimilation. The other aspect would be if we don't assimilate these products, but we could still use them as a quasi-independent verification. Maybe it's a satellite estimate of precipitation. The model from a numerical weather prediction data assimilation forecast produces precip, and then maybe we want to compare to that. And we know that even with our snowfall estimates for winter storms, they're sparse. It's great to have co-op and other volunteer observers, but having, let's say, either a radar product or a satellite product of snow is really helpful to then validate these spatial fields from models. So that's another great use of the products that your discipline's using. And I'm happy to take other suggestions from your disciplines on how we can better integrate our fields.
Right. Yeah, that makes sense. Uncertainty is something we're really working on, and we're not there yet. But yeah, it's an interesting field. Thanks.
Great.
Oh, there's also a question from Lee Dong. Do you want to go ahead and ask that verbally, or would you rather me read it out loud? Jilly or Hilly? I'll just read it out loud. So he said, I probably missed this. Is there an additional benefit from assimilating impacts field campaign observations compared to the regular ground-based 88D radar observations for winter storm prediction?
Okay, so in this case, what is new about the impacts field campaign? So you would have aircraft temperature measurements and moisture. That's something that you might ordinarily have from commercial aircraft, but they generally try not to fly through intense winter storms. So a challenge, I think, for mesoscale predictability is that if airports are shut down and aircraft are hoping to avoid the storm and maybe the turbulence in the storm, you're missing a key data set. Now, you still have satellite and radar, but you're missing kind of the commercial aircraft, which is a good source of the higher resolution data in the upper atmosphere. And then weather balloons, those are only maybe 12 hours apart, except for special launches. So that's one benefit. The other part is the impact field campaign is downward pointing. It's going to be different frequency of radar and other different aspects compared to the operational radar. So our experiment specifically used the difference between conventional OBS and using the field campaign OBS. So what we would almost need to add to answer your exact question is if we did another experiment that assimilated the Z and VR from the conventional radars and compared that to the field campaign, then we'd be able to get you a more exact answer to that question. But that's a great one to follow up on, to kind of go from our experiment that we have and get even closer to a HER-like setting with all the other observations that exist.
Thanks, Isaac. Do you want to go ahead and ask your question?
Yeah, thank you, Kazi. So my question is, you showed a slide that had the shape of the hydrometer as a picture, and then you had sort of a plot on the side. You know, if you look at the image that you get from the CCD, it's a mix of, 3 bullet rosette, 5 bullet rosette, aggregates. And so it's always really a mix of different shapes, but then you have on the side showing that, okay, here we have needle, we have aggregates here and there. So how did you come up with a single, if you can call it a single shape, knowing that you have really a mix of aggregate and other shapes in each column?
Yes, good question. So what we really meant by those labels, and I should have made that clear in the talk, is that we were coming up with different temperature regimes that favor particular habits. But at a particular time when you're sampling, you're going to still have, like you said, either aggregates or needles or other different types of crystals in that regime. So the idea there is to see our different temperature regimes and maybe temperature slash moisture regimes identifiable in dual pol. And so from there, if we're comparing to those images, it's hard to say, how do you summarize maybe the thousands and thousands of snowflakes? You could use AI. There's been some works in the NASA Impact Field campaign that can do some machine learning to try to characterize that. There's also some summary statistics like the size distributions of the particles and the aspect ratios. So that aspect ratio might help whether it's a, let's say, needle or plate. I know you have to consider the angle and all that. But you're right, it is a complex challenge, but we're trying to see what can we learn in aggregate so that we can update maybe microphysics or thermodynamic environment in a model, but knowing that the real atmosphere is so complex compared to kind of the assumptions we might make in the microphysics and other things like that.
It would be very helpful, like, when we are doing forward calculations, for all the sky microwave, let's say, you have to define the shape, and right now we have to do something random, really, mostly sector snowflake, or in the older CRTM, it's just spherical shapes. So it would be really helpful to know what shape you are expecting, or at least a combination of the shapes to define for doing the forward calculations, even if you don't really know the orientation.
I think that would be helpful. And there's others in the ADAPT group at Penn State that are specifically looking at the challenge of microwave data assimilation. So I think having a more robust microphysics and including that and assimilation as well as these type of studies, that's a great idea.
Yeah, thank you. Very nice talk.
Do we have any other questions? You could raise your hand or just type in the chat or just unmute yourself because that's the end of my queue. So Sheila asks, could you tell us a bit about your Mars atmosphere research?
Happy to. So I started actually my Mars atmosphere research when I was a grad student at University of Maryland here, working with Professor Eugenia Kalne. And there we use all these tools. So basically a numerical weather prediction model. It actually has the same dynamical core as the GFS. And we have observations from satellite about twice a day, morning and afternoon. And we actually do ensemble data assimilation. So from there, we reconstruct the state of the Martian atmosphere every hour over about 10 years. And the forecasting challenges for Mars remain kind of the synoptic-scale weather systems, but they could also then spin up into dust storms because we have dust on the surface. And in some cases, those dust storms can grow to cover the planet. And every few years, we get dust storms that go global and last for weeks to months. So the big forecasting challenge for the Martian atmosphere is how do some of these dust storms glow from kind of regional scale to global scale? And why does it happen every few years? And the predictability challenge is maybe how far in advance can we predict these storms and what observations might help? So basically a lot of the similar techniques that we're using for Earth, but applied to Mars. Thanks for that question.
Thanks. Do we have any other questions for Professor Greybush while we still have him? All right. Well, unless I'm interrupted, which as always free to do that. Thank you so much to Professor Greybush for giving us this great talk. Thank you everybody else for attending. We will continue our seminar series next Tuesday. Is that correct? I think we're skipping Monday. Am I crazy? Yeah, yes, because Monday is Columbus Day. So we're continuing it on Tuesday, and that one will be in person. So, okay, great. Thank you, everybody. Have a great day.
Thank you so much.